Welcome to Supercomputing 2017. My name's Ian Buck. I'm the VP GM of Accelerated Computing at NVIDIA. This is my 11th Supercomputing as an NVIDIA employee. I was in 2006, my first talk was actually introducing CUDA at Supercomputing in Florida, and now I'm here in Denver. So welcome everyone. It's been an amazing show so far, and I look very excited to see all these people here. When we started this journey, we came up with this idea of accelerated computing, of taking the best possible CPU and marrying it with the best possible parallel processor, the GPU, to accelerate workloads. We believed that you should run the serial code on the best serial processor available, and the parallel code on the best parallel processor available. This idea was early for its time in 2006 because, well, we were still in the era of Moore's Law. Every year, about every year and a half, we would get a faster serial processor from the semiconductor world and didn't have to worry about performance. But around 2010, we started seeing the end of Moore's Law, and we're living it today. What's great about accelerated computing is that by changing the rules of the game, by not trying to build one processor that runs all workloads, but leaves the best serial processor and parallel processor to optimize differently, we can continue to innovate and provide performance even in a post-Moore's Law era. This year, we have been focusing on launching our latest GPU, VOLTA. It's been an amazing year. We're now in full production with VOLTA. It's an incredible GPU, over 21 billion transistors, basically the largest processor that the semiconductor industry will allow us to make. It has over 5,120 CUDA cores, 7.8 64-bit floating point teraflops, 15.7 FP32, and with the new Tensor Core, we can do AI at 125 teraflops, an amazing processor. It's now in production. It's been adopted and endorsed by every major cloud. Amazon today has it in their cloud. In fact, we have some demos here in the booth that are running on Amazon's cloud. You can get access to this exact GPU for only $3. It's available to you right now with a credit card on Amazon. And coming to all the other major clouds in every country and in every region very soon. In addition, all of our servers, OEM partners, now have Amazon fully qualified. Whether it be Cisco or Dell, HP, Huawei, Lenovo, IBM, Supermicro, everybody has a VOLTA server available for you to buy today. So it's taking off. It's a very exciting time for us. And finally, we spent the year launching VOLTA, and I'm glad to be here at Supercomputing finally to wrap up its go-to-market. In addition, today, Microsoft announced that they're pre-announcing VOLTA in the Azure cloud. You can go sign up today to get access to it. It'll be available in December. And yet another way to get access to GPUs, whether it be in the server or in the cloud. VOLTA is changing the way people are building supercomputers today. One supercomputer that's being built in Japan by the Advanced Industry Scientific and Technology Group in Japan is building a computer called ABCI. When complete, this will be the fastest supercomputer in Japan. With 4,352 voltas, they're going to achieve 37 petaflops of 64-bit precision. But they're also reaching a half an exaflop of AI. And this is how these computers are talked about today. They not only are just computers for simulating with 64-bit floating point, but also for doing AI, for processing the data and output of these simulations. They're both simulation and AI supercomputers. NVIDIA has also announced that we're building a new supercomputer. Last year we talked about Saturn V with Pascal. We're building a new supercomputer right now called Saturn V with VOLTA. It'll be 660 DGX nodes with over 40 petaflops of peak performance and 660 petaflops of Tensor Core AI performance. This computer is being built to help develop the first AI self-driving car. We use this computer inside of NVIDIA to simulate real-world experiences safely inside of a computer instead of on the real road, and train and teach an AI how to respond in life-threatening or critical situations to make the right decisions. You need supercomputing both to simulate a self-driving car and to train and teach a neural network how the car should behave in real-world situations. And we're excited about this computer and many others. What makes these computers so amazing is that they are built around strong nodes. Unlike traditional COTS supercomputers, where you might have thousands of very small CPU-only nodes, a GPU supercomputer tends to be built of strong nodes. 2 CPUs with either 4 or 8 voltas in them. By bringing the computing power into the node, we can achieve much better strong scaling in the performance of applications and with fewer nodes. So we spend less of our money on networking equipment, on scale out, and can achieve better performance because we're trying to scale over fewer nodes. What does this mean for real science? Here's a simulation of amber on a new molecule called CRISPR. If you haven't heard of CRISPR, you probably will. It's basically the bio machine that's responsible for splicing of DNA in our bodies. If we can understand how CRISPR works and simulate it and study it inside of the computer, we can have a hope of actually solving some of the genetic diseases that face us, as well as cancers and all sorts of other genetic-related diseases. Many Nobel Prizes are coming with a discovery around CRISPR. Simulating this molecule with traditional CPU servers is actually quite challenging, and as they try to scale up, there's limitations to the strong scaling. In fact, at around 40 nodes, the performance starts to tail off. And once you get out to 100 processors, you're really at the limit of what you can do in strong scaling with simulating CRISPR with Amber. However, with one node of 4 voltas, we can achieve the performance of almost 10 times of that supercomputer. And this is also at the cost of only about 5 of those CPU nodes. So by moving to a strong scale architecture, we can achieve much higher performance and with much less cost. And that's a big part of why accelerated computing today is popular today and why it's driving so many supercomputers around the world. We've been at this for a long time. We've been building our platform for the last 10 years and helping the community port applications to GPUs. Today, we're actually very excited to announce that the top 15 applications in HPC are now GPU accelerated. From VAST to games, we have all the major HPC applications. In fact, our application catalog now, which keeps track of all the applications that have been ported to GPU, has crossed 500 apps. We've really reached a tipping point in accelerated computing where no supercomputer today isn't running applications and a meaningful workload that could be accelerated with GPUs. We've also been working on the developer tools. When we started with CUDA, we launched CUDA 1.0 in 2007. We're now on version 9, which supports VOLTA. It's a big part of what we do is engagement and providing the best tools for the developer community. CUDA 9 brings VOLTA to CUDA, gives access to tensor cores, supports NVLink and the new stacked memory. It has new libraries for matrix multiply, new libraries for image processing and processing image data. That's our MPP library, and also improved FFT optimizations for signal processing. We've added new compilers, support new OSs, and new profiling tools to really help you understand where your application is spending time. All of this is available for free on developer.nvidia.com. In addition, we're expanding our programming models, thinking about new ways to program our GPUs, to keep them busy, to restructure our codes, and to build a higher level, more domain-specific, potentially, programming languages. To enable that, we offer cooperative thread groups, which allows the different SMs to actually talk directly to each other and execute in parallel while coordinating, while synchronizing. We've also been investing in OpenACC. This open programming environment is a directive-based approach, similar to OpenMP, except much simpler in the sense that you simply state that this loop, this Fortran block, can be executed in parallel, and let the compiler try to port it and move it to the GPU. We launched OpenACC many years ago, and it's actually grown in adoption quite a bit. It now supports not only NVIDIA GPUs, but Power CPUs, the Sunway supercomputer, which is the #1 supercomputer in the world, x86 CPUs, Xeon Phi, AMD, even PEZY, all have support for OpenACC. You can write one application, and it runs on all of these architectures. In addition, it's performant. It actually runs quite well on both CPUs and alternative MPI implementations. And then when you take that same code, no modifications, and run on a GPU, you get the amazing speedups and benefits of VOLTA as shown here. The #1, #2, and #3 top HPC application are actually programmed with OpenACC. So if you're a little uncomfortable with programming the GPU directly in CUDA, I highly encourage you to give OpenACC a try. It's freely available with PGI's compilers, and their booth is right next door. The amazing thing about accelerated computing is what you can do compared to the alternative. Here is a typical mixed workload supercomputer. Here I'm running VASP, which is a material science code, AMBER, which is a life science code. I talked about CRISPR before, MILK, which is a quantum physics code, and I'm doing a little bit of deep learning. If I look at a typical rack of 160 self-hosted servers, that might, 4 racks might consume upwards of 96 kilowatts in a high-dense HPC kind of environment. By moving these work applications to a GPU system, I can achieve the same performance with only 1 rack. In fact, it's only 12 accelerated servers, each with 4 V100s. The whole thing runs on only 20 kilowatts versus the 100 I had before. So I've saved not only 1/3 the cost, but 1/4 the space and 1/5 of the power. The power savings alone can pay for many for these new servers in just a few years. This kind of savings is kind of why people are adopting accelerated computing, why people are using strong nodes instead of weak nodes to deliver the same amount of throughput per budget or even higher. We have a demo here in a booth that lets you play with this. You can try in different workloads, your favorite applications, and see the effects of the differences between CPUs and GPU nodes. People are also doing amazing things in AI. The AI world is changing so fast, and these supercomputers are allowing them to achieve new world records in AI. This is a neural network called ResNet 50. It's kind of a modern neural network used for image classification. What's inside this image? This is one of the ImageNet winners from a few years ago. In February of this year, just this February, it took 4.4 hours to train this neural network on a bunch of Titan X's. Then in June, Facebook figured out how to train this in only 1 hour on 256 P100s, basically their version of Saturn V. Then in August, IBM with the Power 9 system beat that by 48 minutes. And then just recently, actually last week, PFN, Preferred Networks, figured out how to strong scale ResNet training up to 1,024 P100s to train this neural network in 15 minutes. To put that into perspective, a year ago, it took a week to train this neural network. The changes that are happening in AI are amazing, and it's probably because of the access and availability of AI supercomputers that are allowing people to figure out new neural networks, new ways to train. And of course, now that we've conquered ResNet 50, they can make this network even bigger, even more complicated, even smarter to build even more, and give it more time to train. AI is also a tool for science. It is not just for the Googles and Facebooks and Amazons of the world, but it also can be a tool for science. Here's an example, for instance, where you can combine simulation and AI to do scientific discovery. We work with researchers who are looking for gravitational waves. This is actually when 2 black holes collide. They're actually, as they approach each other, they start spinning rapidly around each other. These 2 massive black objects are spinning. Actually, you can't see it, but the gravitational waves they emit are massive. We can simulate what those waves should look like inside of a supercomputer using our GPUs, using the 64-bit precision. We can then teach an AI to recognize how to identify those gravitational waves in the background of cosmic radiation. By taking the output of the simulation into an AI, build a gravitational wave black hole detector. Then we can actually go look for it. Take the data, both simulated and from real world, to prove that our neural network is correct, and then run inference on all of the data that we've collected from sensors around the world to find these black holes, these invisible things hundreds of millions of light years away, but are doing very slight gravitational tugs on you and me right now that we don't know. We can study these things from so far away. It's truly amazing. This is work done both for HPC simulating and in AI, all on the same supercomputer at Blue Waters. A great combination of doing simulation and AI. And notice the different kinds of precisions. A processor needs 64-bit floating point. Some of it can be done in 32. Training is a combination of 32 and 16-bit. And for inference, we can do stuff in 16-bit and 8-bit. It's one of the reasons why we're building one processor for both HPC and AI is because of this use case of being able to have all those different workloads. There are many stories of people doing really interesting work in HPC and AI. I'm not going to go through all of them. It would take me too long. The Princeton work for particle physics is really amazing. They've using TensorFlow to try to detect when a fusion reaction inside of a fusion reactor might go unstable. If they can detect when it's going to go unstable within 10 milliseconds, that's a big enough window, just 10 milliseconds, to have this microwave injector injected with the right amount of energy at the right frequency to stabilize the reaction and keep it going. If we can figure out how to stabilize fusion, we can actually maintain a sustainable, ongoing fusion reaction and actually create and make fusion energy viable. Using AI, they actually increased their accuracy by 50% to get to 90% accuracy of fusion failure events. They're not all the way there yet. They need to get to 100%, but AI is their path forward for doing that. Many other of these stories have been blogged about. They're on our website. Go check it out at blogs.nvidia.com. To help the AI industry world get access to the latest frameworks, about 2 weeks ago, NVIDIA launched their GPU cloud. This is a container registry that offers all the major AI frameworks that's NVIDIA tested and optimized and available on our website. You can actually go download it right off the website today. They're totally free. We made these available by containerizing the frameworks. These are really huge academic pieces of software that are very complicated, many different dependencies. But by using containers, it's very easy to use. Here at HPC, we're announcing that we're also going to make available HPC containers. These same container technology can be used to simplify deployment of HPC applications. So we worked with the community to containerize HPC applications, put them up on our website, free to download. So really in 3 steps of downloading, signing up, downloading, and running, you can actually run any one of these HPC applications instead of having to actually install and try to build it on your system. We've started with 5 major applications: Games, GROMACS, LAMPS, NAMD, and Relion. Those are available on our NGC cloud right now. You can go download them. We're also working with the community to add more in the areas of bioinformatics, CFD, material science, physics, and seismic. We're not just stopping there. We're also going to work on containerizing HPC Viz. Visualization is a key part of science. When you're studying something like this rocket nozzle that's planned to actually take people to Mars, the complexity of the combustion happening in here is so deep that we can't just rely on a computer to tell us how to design it. A human has to observe and see and understand the vortices and how the chemistry is actually happening to make improvements to this rocket nozzle. Visualizing incredibly large data sets like this one is an important part of science. In addition to the HPC applications, we're also containerizing HPC Viz. We'll offer 3 different containers, all based on the common HPC software called ParaView. One of which will be with NVIDIA Index, which is optimized for visualizing volume data, like I just showed, combustion data, cloud data. ParaView with NVIDIA Optics, which is NVIDIA's optimized ray tracer that will create beautiful looking images, both to help you get full fidelity in your science to see the object with full shadows, fully rendered, and also to make some amazing pictures, which hopefully can help you raise money and funds. And finally, NVIDIA ParaView with Holodeck. This is a real-time rendering engine that is optimized by NVIDIA to provide real-time interactivity, real-time shadows, and complicated real-time surface materials. So you can make not just flat-looking OpenGL renderings, but the kind of renderings we see in modern video games and movies today are now available to the HPC Viz researcher. 3 different containers, all for different use cases, all for free, downloadable on our NGC website. So with that, NGC is really becoming a container store for both our deep learning containers, if you want to do deep learning, HPC applications, and visualization applications. We've tested them all on Pascal and VOLTA. They're available now, whether you want to run them in Amazon's cloud, on your DGX, on your Linux box, they're available to you. And that's it. So our mission has this year has been to help bring VOLTA to every cloud, every computer maker in every country. And I think we've achieved that here finally at Supercomputing. And I encourage you to walk the show floor and see the different servers available with VOLTA to buy or in the cloud. Deep learning really is coming to HPC. Go discover some of the different AI use cases here at Supercomputing and some of the amazing supercomputers that are being built. And then finally, I encourage you to check out our demos on the GPU cloud to try out your favorite HPC application or visualization. We have some amazing demos here. You can go see what a gravitational wave actually looks like and visualize it and spin it like I talked about here. We have also shown how AI can improve scientific simulation in molecular dynamics by using AI to predict some of the quantum fields that are necessary to do accurate molecular dynamics. We obviously have our visualization containers. You can play with some of these real-time interactions and the HPC containers and actually visualize and see NAMD running in real time. ANSYS is here, and they actually have a real-time fluid simulation programs that let you actually change the mechanical models of things and see how the fluid the interactions with waves and airflow can happen over a wing in real time. And finally, if you want to play with your favorite app and see what its value is compared to a CPU versus GPU system and test the math, you're welcome to do so. The booth, that demo is right around the corner. You can plug in your favorite app and see how fast it is and what your supercomputer could look like should you choose to buy one. All right, well, thank you, everyone, and I hope you enjoy the rest of Supercomputing and enjoy our booth. Thank you.